Greetings, fellow learners. In this video, we are going to talk about feature pyramid networks, the what, the why, and the how with some code. So let's get to it. So feature pyramid networks are an architecture enhancement to convolution networks to add scale awareness. And this improves the performance on many computer vision tasks like object detection, segmentation, and others, while only adding modest computation and memory overhead. And it does this by building a pyramid of feature maps at multiple resolutions, and hence the name over here. So that's feature pyramid networks. Now, I'm going to discuss the intuition of why we need something like this, specifically looking at the problem of object detection, but just note that it can be applied to other forms of computer vision too, and hence this is kind of why these feature pyramid networks became so popular and why we're talking about it right now. So object detection. Now, this essentially involves a localization, that is where an object is, and classification of objects in an image. So sometimes the objects are large, other times they are small. And so any object detection framework or system needs to be scale invariant. So how do we deal with this and solve this problem? Well, back in like the 2000s, sliding window approaches to object detection were very popular. And so what this means is we have like this little sliding window for an input image here. And they determine like all these past types of object detection frameworks would determine if there is like a dog in this window. And hence we would classify, this is the probability there is a dog in that window. We would then slide this little window and ask the same question. Is there a dog in this window or a cat? Then do the same as we slide this little fixed size window across the image. And you can imagine here, though, to handle scale variance, like it's not going to be very great because if a window is about this big on this dog that's bigger than the window, it probably might not recognize it as a dog. And so, hence, it's going to be a little bit less accurate. To handle this, though, these older sliding window approaches would use something called image pyramids. That's basically take the input image and then scale it at different levels. So this is 100%, 80%, 60%, 40%, right? And then what we would do is apply the same fixed size window, let's say it's like 19 by 19 pixels, across each of these images. And as we apply a sliding window, you can imagine that, this sliding window and this entire structure over here would be better at detecting much larger objects, whereas this one over here would be better at detecting much smaller objects. And so that's how these 2000s, like the wavelet approaches, the histogram of gradients, the deformable parts models, they kind of did this mechanism in order to get away with scale invariance for object detection. Now, in 2013, with the rise of neural networks, GPUs, and data, we eventually culminated with R-CNNs becoming the state of the art for object detection. So R-CNNs would perform object detection in three main stages. So we take an input, we would determine region proposals, like 2,000 bounding boxes of potential objects. We would then warp those objects to fixed sizes, pass it through a CNN architecture to get just this, like a vector, and then classify this with this SVM classifier in order to get the final localizations and classifications of objects in an image. Now, for the scale invariance piece, convolution networks exhibit like some semblance of scale invariance due to the pooling operation. And on top of this, cropping plus warping these region proposals also really address the scaled variance issue. Because you can imagine if there's like a small object region proposal here, it's going to be warped to some fixed size so that it can be effectively detected and encoded by this CNN. And hence, that's how R-CNNs kind of got away with this scale variance issue. But the issue now, another issue, was that, well, it's very slow. And honestly, it's so slow, it took like 50 seconds to make an inference on a single image, even on a GPU. And a lot of that like lag was mostly because of this warping plus feature transformation phase here. So how do we deal with this? Well, in 2015, we had the Fast R-CNN introduced to kind of get rid of that warping phase. So what happened was we take an image, we generate region proposals, kind of like how we did previously with like selective search, some algorithm. Then what we would do is we would transform this image into a fixed size tensor. And it's going to be, let's say it's like a 14 cross 14 cross 512 tensor. And then we would just take like subtensors within this that represent each region proposal. We would use something called ROI pooling to transform that variable size tensor representing a region proposal to a fixed size tensor, like 7 cross 7 cross 512, and then eventually get the object localizations and classifications. This was much faster at 2 to 3 seconds for inference per image on a GPU. So that's great. Now, this issue, though, is that it's not scale aware as much anymore. It is somewhat scale aware because of these convolution activation pooling operations, but not very much in the sense that we remove the warping logic that actually helped add that scale awareness. And so what we'll end up with now, an issue here, is that, this tensor, this single tensor that we have, it might be too coarse to detect small objects. Shortly after this, we actually had faster R-CNNs introduced, which further sped up network inference to like 300 milliseconds per image on a GPU. And it did this by removing the selective search region proposal generation and replaced it with an RPN, that is a region proposal network to generate bounding boxes around potential region proposals. And now with this end-to-end trainable neural network, it was able to generate images or generate like object localizations and classifications very fast. Now, while this is fast, it still is not as scale aware because of the same reason we mentioned with Fast R-CNN. We have this coarse tensor, the single tensor that is a representation of this image, and it might be too coarse to detect small objects. So how do we really solve these problems that we see with fast and faster R-CNNs with scale variations? Well, one thing we could think of is using image pyramids. But the problem with using image pyramids is that it leads to increased memory utilization and also computation slowdown during inference. And this would negate the fast and faster aspect of these networks. So the original papers, if you read them, they actually don't use image pyramids and instead would try to just resize the input image such that the shorter side is 600 pixels or something like that. And so what we need is a mechanism for faster R-CNN to detect objects of varying scales and also not incur extra computation or memory costs. And feature pyramid networks can really help with this. So I hope all of this builds up with the historical aspects of object detection really help paint the picture of why these feature pyramid networks can be very helpful. So let's now actually talk about what this is and how we can compute these feature pyramid networks. So when we're trying to do object detection via fast or faster R-CNN, we would want to pre-train the convolution activation pooling parts of the network, the CNN parts of the network, using the relatively simple problem of image classification. So that's you take an image that's over here and you get the object category of the image itself. And this is the entire network over here. Each convolution block is basically a convolution activation and pooling operation. So you can imagine we take an image, we transform it into a 32 cross 32 cross 128 tensor. This is again convolution activation pooling. 16 cross 16 cross 256 tensor, conv activation pooling, 8 cross 8 cross 512 tensor, FC head to get the dog. And the entire goal of feature pyramid network is, instead of generating one tensor that may be too coarse for further processing, we generate multiple tensors of varying resolutions instead. And this is how we can do it. So first, we take an image, we generate these tensors over here by a forward pass. We can then take this 8 cross 8 cross 512 tensor. We will then perform some upsampling. Upsampling is basically done through like bilinear interpolation. So we're going to fill in values effectively to scale it up twofold along the width and the height. So you end up with a 16 cross 16 cross 512 tensor. Now what we want to do is we want to kind of add this information to the information that exists here in this 16 cross 16 cross 256 tensor. And to add them, we need to make sure that the channel sizes match. And this is why we perform like a pointwise convolution to adjust the depth over here. So we get 512 channels. Tensors of same shape can be added. And so we add them to get this tensor here. And, because of upsampling, we might get like certain artifacts due to upsampling itself, the jaggedness or the unevenness within this tensor. And in order to clean up this operation and smooth out the artifacts, we will use a 3 cross 3 convolution here. And using this, we'll end up with a 16 cross 16 cross 512 tensor with appropriate padding and a stride 1. So now we have this tensor here. We will then do the exact same thing that we discussed before. We perform upsampling 2x to get 32 cross 512. Make sure that the number of channels here, 128, also becomes 512 using a pointwise convolution. We'll take the sum, then we'll also smooth out the artifacts of upsampling with 3 cross 3 convolution to get this tensor. So you can imagine now, instead of just one coarse tensor, we now have 3 tensors of multiple resolutions that can be used for further processing. This is the coarse tensor, which can be great for generating or detecting larger objects. And this is the finer tensor, which can be used for detecting much smaller objects. So let's now take a look at this in the entire Faster R-CNN training pipeline. So for Faster R-CNN training using feature pyramid networks, we first pre-train the network on the classification task. So given an image, determine the classification of that image. We're going to be training these convolution activation pooling layers first. Next, what we do is, this entire thing is going to be the training of the original Faster R-CNN. So take an image, convert it into this single tensor that represents the image, pass it through the region proposal network to generate, region proposals, places where object of interest may exist. For each of those region proposals, we'll then perform ROI pooling to eventually generate object localizations and classifications. And then we'll compute losses here. Now, if we add the FPN model, we're going to get this modified network instead. So that is, now we have an image. Instead of just generating one tensor, 14 cross 14 cross 512, we can generate like multiple tensors, in this case 3 tensors. One of 14 cross 14 cross 512, then 28 cross 28 cross 512, and 56 cross 56 cross 512. One is good for representing coarse features, the other for much finer, smaller features. And hence, what we're going to do is I put little notes on these two. So we're going to pass in all of these, like each tensor will be passing through this region proposal network in order to get like 1764 predictions, bounding box predictions. So this is like 1764 predictions for each of these 3 tensors effectively. Now, we will use for each case, like a subset of these, like 256 of them, making sure like the positive and negative boxes actually kind of are similar in number in order to generate the RPN loss. And then what we'll do is, we have like 1764 predictions. We multiply it by 3. We can combine all of them together. And I see I put a little note over here to indicate that we are going to be now combining all of these tensor scales. We will then use NMS in order to remove very highly overlapping bounding boxes and eventually end up with 1,500 proposals of such, right? We will now then, because this is training, we will only consider 256 proposals, such that, the number of positive and negative classes of these boxes are kind of comparable to each other. We will then take each of these 256 proposals and pass it through this next section of the network. We will take, so that's one region proposal will be passed here, and all of these object scales, all of these tensors are going to be passed into this section here. We then have this part called the tensor selector. So based on the region proposal we're dealing with, we are going to select the appropriate tensor, which we want to use to encode the image, right? So you can imagine for the idea is that this tensor selector for very small region proposals, we will use the much finer tensor of 56 cross 56 cross 512. And for much larger region proposals, we want to use the coarser tensor of 14 cross 14 cross 512. And effectively, once we select the tensor, the working is exactly the same as it was with the original faster R-CNN. We could process this entire path and we'll generate, 256 up to 256 bounding boxes. And then we can generate a detection loss, compute the full loss, and then perform back propagation. So that's kind of how this entire FPN module can be added over to faster R-CNN. Now, we talked about this tensor selector and how it should kind of select coarser or finer tensors depending on the region proposal. But how does it actually do that? Well, kind of cleaning up the mess here, the tensor selector will take different tensors of the image of different resolutions. It'll take a single region proposal over here, and then it will determine the appropriate region. It'll determine the appropriate tensor scale to use. And the way that it does this is typically by some heuristics, right? So, and a heuristic that is kind of used here is this single line formulation. So K is the scale of the tensor used. So for example, this could be K is 1, this is K is equal to 2, this is K is equal to 3, for example, right? Now, K0 is basically the number of scaled tensors, 3. Now, this log term, you have WH, right? W cross H is the pixel shape of the region proposal, how large, how wide, and how tall it is in pixels, that specific region proposal. 224 is just a reference size, and this is mostly because the pre-training, I think, for this case might have been for images of size 224 cross 224. And why we even have this formulation is the intuition is larger region proposals would use, they would have, let's say if we have a 224 cross 224 image, W cross H would be the region proposal is basically the entire image itself, right? This is the maximum it can be, 224 cross 224. So you can imagine this term becomes 1, log of 1 base 2 becomes 0, and hence K is equal to K0, which is equal to 3, which you can imagine this to be the coarse tensor. So, which makes sense. Large region proposals, coarse tensor. Now for smaller region proposals, let's say the width and the height, you can imagine it's going to be 1 pixel by 1 pixel at most, right? And if you kind of apply this, it would be log 1 divided by 224 to the base 2, which would be K0 minus 7.8. And this could give negative 4.8. We can clamp this to K is equal to 1 because it has to be 1, 2, or 3. And this would be the fine tensor. So we have the coarse tensor for large region proposals and the fine tensor for small region proposals. That's kind of the intuition that we wanted to go for anyways. And this is a nice heuristic to get to that point. And just note that you can change these values. This is just one of probably many ways you can frame this heuristic and hence select tensors. Now, let's talk about inference with faster R-CNN. So with the normal faster R-CNN, we would take an image, we would generate this single tensor, like 14 cross 14 cross 512, generate region proposals over here using, NMS, and then get like 300 region proposals. For each of these 300 region proposals, perform ROI pooling, and then we're going to get like localizations and classifications. Now, if we added FPN to this, it'll look now like this, where we take an image, the VGG plus FBN backbone is over here, in which case we will be able to generate 3 tensors of multiple dimensions. All of these 3, we'll be running the region proposal network to generate 1764 predictions for each of these tensor scales. There'll be so as many thousands of these boxes that overlap. We'll only get like the top M. Let's say it's just 300 proposals. Now, for each of these 300 proposals, we're going to run this little block. We're going to take one region proposal, pass it here. We're also going to take all of these tensor scales, pass it here. And we will generate with this tensor selector only choose one of these 3 tensors. For smaller region proposals, we're going to choose the much finer one, like this 56 cross 512. For larger ones, it might be this coarse tensor over here, based on that heuristic. So we select that tensor. We're then going to be able to generate bounding boxes and localizations, use NMS to get the final results. And that's the inference over here. So I hope at least the working and methodology of feature pyramid networks used with faster R-CNNs kind of makes sense. And now to kind of hammer home the performance enhancement that this offers, we have some code to compare basically the case with feature pyramid networks and the without feature pyramid networks on object detection. And specifically, we're doing pedestrian detection over here. So with pedestrian detection, we've created essentially 2 classes. One of them is going to be we're going to get faster R-CNN with the ResNet backbone along with no feature pyramid networks at all. So it's basically like a ResNet over here. And the backbone is simply just going to be a sequence of convolution activation pooling layers. And then we have another, which is getting faster R-CNN with ResNet with feature pyramid networks, right? So it's essentially going to be the backbone that's created over here using let's say 3 of these scales, right? 3 scales. And then we use this as the backbone for our faster R-CNN. And then when we actually draw comparisons between the two, we're training them for the same time on the same data, and then we're running them on the same evaluation set. You can see here that with no FPN, the precision and recall are lower than that with actually using feature pyramid networks. So effectively, feature pyramid networks can increase precision and recall of object detection. And honestly, if you just wanted to look at some examples here, this first image is the ground truth. This is going to be without feature pyramid networks. This is with feature pyramid networks, right? So this case, they kind of perform the same. This case, you could see it's a little bit better as, the feature pyramid network case would better encapsulate the person. This case, there's this extra box here for without feature pyramid networks. This case, there's multiple extra boxes here, whereas here with FPNs, it's a little bit more clean. And so I hope you can see kind of how, using feature pyramid networks could actually enhance performance of your convolution network on this case, it's just object detection, but it could have been segmentation or anything else that requires a lot of scale awareness. So hope that all makes sense. Quiz time. Have you been paying attention? Let's quiz you to find out. Why use feature pyramid networks in object detection? A, to reduce the number of trainable parameters. B, to detect objects of different sizes in images effectively. C, to improve the performance of detection. Or D, to reduce memory consumption of detection. I'll give you a few seconds to answer this question. The correct options are B and C. Did you get them right? Please comment your reasonings down in the comments below and let's have a discussion. And at this point, if you think I deserve it, please do consider giving this video a like, because it will help me out a lot. Now that's going to do it for quiz time, but before we go, let's generate a summary. In this video, we took a look at feature pyramid networks, which is an architecture enhancement to CNNs to add scale awareness. And this can improve performance on object detection and segmentation while only adding modest computation and memory overhead costs. We observe that for cases like the fast and faster R-CNNs, when we take an image, we only encode it into one specific tensor size, and this may be too coarse to detect small objects. We see this as an issue with the fast R-CNN, as well as the faster R-CNN too. To deal with this, we could have used image pyramids, but then this would increase memory and computation utilization. So to preserve the aspect of being fast and faster, we instead use something called feature pyramid networks. So we discussed then the computation of how we can take an image and instead of encoding it into one single tensor, we can encode it to like multiple tensors of varying scale. This tensor of 8 x 8 x 512, for example, could represent and be good for detecting very large images or large objects within the image. And this 32 x 32 tensor can be better at detecting much smaller parts in the image. We then talked about how we can train the faster R-CNN first, without FPN, and then compared it to the case with FPN. And we have this like tensor selector, and how we actually do this, we discussed as well this heuristic over here. We then talked about inference again without FPN, and then with FPN as well. Finally, we looked at some code comparisons to actually draw comparisons both like without FPN and with FPN just to see how adding this feature pyramid network backbone can actually enhance performance. And so yeah, that's kind of all I have for today. So all of the resources, the code, the slides, everything will be down in the description below. There was many kinds of research that I've highlighted here, from the old object detection with like sliding windows to like the R-CNN family. And I have in each case, I have like videos to describe the R-CNN, the fast R-CNN, and the faster R-CNN in the playlist, which I will link down in the description below. So do check that out for more resources, and I will see you in the next one. Bye-bye.